All right, so I'm going to go ahead. I'm going to break down the quantum numbers for a wave mechanical description of the atom and orbitals. And this is going to be really simple. Pretty much the exact same thing you learn in high school chemistry with the orbitals, but now it's just designated a little bit fancier. So real quick, I haven't done a video on the Bohr model yet. The Bohr model is very concrete. It has precise values, but they're not necessarily accurate in every scenario. You got a lot of things right. I might go into that later and all those values and the equations. But for now, we're not going to talk about that. With the wave mechanical description of a model, things are less concrete, right? We work in probabilities and all that. So we can't say for sure where the atom is or where the electron is, where the nucleons are, whatever. But we have probabilities. We know where they could be. That's what these orbitals are. When we're designating an orbital, we use 4 quantum numbers, which is what I'm going to go over. And we'll just start from the top, right? So we have our in quantum number, the total quantum number, or the principal quantum number, which is, can take on any value from 1 to infinity. It won't take on a value usually higher than maybe 7 at most. And sure, as we get new elements, that will go up. But so in is analogous to the shell, right? In high school chemistry and everything like that, we were taught, okay, so we have the 1s shell. Now we have the 2s and the 3p shells, or the 2p shell, which is the second shell. And then the third shell has these 3, the d subshell added. Then the fourth has the f, then g, and then so on and so forth. So in can take any value. If I were wanting to represent this shell right here, the 1s orbital, then I would say n is equal to 1. So it's completely analogous to the shell that you're talking about. And then we also have our L, which is the angular quantum number, angular momentum quantum number. And now there are a couple different values this can take on, and we can look and we can notice a pattern. So L has values that range from 0 to n-1. Okay. What this means is that the higher quantum number, the higher the angular quantum number is, kind of the stranger these orbitals will be, these subshells will be. So when n is equal to 1, the only value that L takes is 0. And 0 angular momentum means we have a perfect circle like this. And right, it doesn't orbit around in that circle. It goes anywhere up in between. But that's okay. If we're in the second shell now, we have 0 and 1. So there is an L subshell equal to 0, and there's an L subshell equal to 1. And it just so happens when L is equal to 1, we get these P subshells. Okay. And if n is equal to 3, now we have 3 values of L. Of course, our 0, our 1, and now our 2. And right, that keeps going on. So in practicality, what this one is telling you, the angular quantum number is telling you, is it's telling you which subshell. So this is, right, this tells us the shell, right? This tells us the shell, you can't read that. This tells us the subshell here. Perfect. So, right, if I were to want to talk about maybe 3p, right? What would I do? I would go ahead, I would, oopsies, sorry. I would try to erase, I can't do that. I would just say that n is equal to 3, right? And L is equal to 1. That's talking about this set of subshells, right? Really simple. Then there's 2 other values. There's the magnetic, so they're both magnetic quantum numbers, and one is the orbital magnetic quantum number, which is denoted, second, it's denoted ML. Okay. Now this will specify the exact orbital. right? The exact orbital, whatever one we want. And this goes ahead, this takes on a value for every value of L, it takes on another set of values. It takes on values between minus L, then minus L plus 1, all the way to 0, right? Dot, 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 all the way to L. This makes perfect sense. Because if L is equal to 0, then we just have 0. If L is equal to 2, we have 0, minus 1, and 1. Minus 1, 0, 1. If L is equal to 3, we have minus L plus 1, 0, 1, L minus 1, and L, right? Really simple. And so that means that there are approximately 2L minus 1 values of ML. Okay, really simple. And then the last one we have is MI. So this is the magnetic spin quantum number. So ML right here. At this point, we can already talk about a specific orbital. But if we want to talk about the specific electron, then all we have to do here is take MI. And this can be either plus 1/2 or it could be negative 1/2, right? Because an electron either has a plus 1/2 spin or a negative 1/2 spin. And so we can talk about now with these 4 sets of numbers, right? We can talk about a specific electron in a specific orbital and a specific subshell in a specific shell. So if I wanted to go through, I'll get rid of this, right? So as an example, I wanted to talk about an electron in the 3rd shell in, say, this, the 3rd shell in this subshell here in this orbital. So what would I do? Well, I would set n is equal to 3. And we are in, this is 0, this is 0, this is 1, this is 2, L is equal to 2. Okay, and I want to talk about this one here. And this middle one here, and I might be, maybe I'm wrong on this. Maybe it's not centered. I believe it's centered. And this middle one here would just be 0 as well. Right? Perfect. Because this would be L minus, this would be minus L. This would be minus L plus 1. Right? This would be 0. So on and so forth. And then if I wanted to talk about the electron with a positive spin, I would just put positive 1/2. Now, you might be wondering, right? There can only be 2 electrons in an orbital. Why is that? Well, so the Pauli exclusion principle, right? We can either say that there can only be 2 electrons per orbital, or more precisely, we could define it as there can only be, or there cannot be an electron with the exact same quantum numbers as another electron or particle, as whatever, which is perfect because that means that we could have 2 per orbital, but nothing more, nothing less, or something less. There can be something less, and that perfectly describes what we see in the real. That is pretty much what I wanted to go over for this. So just as a quick recap, this stuff is really simple. As a quick recap, N designates the shell. So of course, like 1s would be smaller, right? This doesn't really have a specific place for the shells here. But right, they're just different sizes, different energy levels, right? And it's pretty much focused on the energy levels. L does have an effect on the energy level. It's more minor compared to the N. And then this pretty much doesn't have an effect as far as I'm aware. But yeah, so basically, right, this is the shell. Let me lower my mouse's sensitivity real quick so I can actually write. This is the sub shell. And then this is the actual orbital, right? Orbital. And then right here, what we have is just a spin. So we can talk about a specific electron if we want. And that is our quantum numbers on the basics, right? The only thing you need to understand this is a knowledge of orbitals, which comes from like a high school chemistry class or just reading a book, you know. So yeah. Anyway, I hope this helped. I might go over a couple other things, maybe Russell-Saunders symbols, Bohr model of an atom, and I might actually break into some equations, as those are very interesting. But I wanted this to be really simple as a starting basis. Anyway, thanks for watching. I will see you guys next time.